So what we're going to be looking at here is we're going to be looking at moments of inertia and centers of mass, and we're going to be using double and triple integrals in order to actually find them. So what we're going to first think about is we're going to think about, well, first, before I say anything about that, if you don't know what a moment of inertia is or what a center of mass is, what you want to do is you want to go back and watch the video that I put together on moments and centers of mass in 1 dimension, 2 dimensions. Okay, the basic ones where we have a constant density. Okay, because I'm going to kind of be referencing a lot of that kind of stuff for this particular conversation. We'll still talk about what exactly a moment is and what a center of mass is, but I go a lot more into depth onto the concepts there, and it really kind of helps to kind of facilitate the whole conversation about moments of inertia and centers of mass that we're going to be having now. All right. So one thing is that you first want to imagine that we do still have a lamina, and so a lamina is this 2-dimensional figure. Okay. But what we're going to be looking at now is we're going to be looking at, I have a lamina, so this very, very, very thin membrane, but its density is not, in fact, constant. And since this density is not constant, we're going to have a function. It's going to be a function of 2 variables because that lamina is on 2 dimensions, so it's on the xy plane, and so we're going to need to utilize that function. And so consequently, you should be thinking to yourself, okay, so I've got a function, right? Okay, that is demonstrated over an entire area, a 2-dimensional area, right? And that's really a double integral. So the area gets represented by the double integral, and then we have the function, and so we'll evaluate that function over that area, right? And that's kind of the idea that we've been working with double integrals. After that, what we're going to do is we're going to imagine what if we have a volume or a 3-dimensional figure, and we want to figure out where the center of its mass is, okay, and where are its moments. And so consequently, since we're dealing with a volume, we are going to be working in 3 dimensions. Right. And so we'll utilize a triple integral for that, and that'll also be allowed. We'll be allowed to kind of work with that if we have a non-constant density as well. Okay. So what we're going to do is we're going to play with these ideas of the moment of inertia, the center of mass. Okay. They're going to really they're going to parallel our work with double integrals and with triple integrals, and also with the work that we've already done with moments and centers of mass already. Okay, so let's talk about moments of inertia and centers of mass, and let's first talk about the mass of a lamina. Okay, so we want to imagine, remember that the lamina is a 2-dimensional, it's like a 2-dimensional figure, okay, like our region D, okay, very, very thin, so the actual, it can be treated as if it's a 2-dimensional figure, okay, and the mass of the lamina, right, we remember if we talked about mass always equals, it's going to equal the density, okay, times, in this case, it'll be the density times the area. If we are looking at, for example, if we're talking about 3-dimensional figures, right, mass is going to end up equaling density times volume. So if I look at this here, I've got this figure, okay, I've got this figure here, all right, and so basically, if I call this region, we'll call this region D, okay? The area of D is equal to the double integral dx dy, 1 dx dy, right? Okay? Now, we'll look here and we'll say, okay, suppose our density function, because we no longer have a constant density function, suppose the density at the point xy is equal to rho of xy. So that's our density function. So consequently, our mass is going to equal this area times density, okay? And so that's going to actually be the double integral. It's going to be rho of xy dx dy, okay? Now, I know, right, we're like, oh, okay, well, why isn't it just rho of xy on the outside of the double integral? Well, what we want to imagine is that essentially this rho of xy is like a function that gets evaluated on the entire area. So we want to imagine that if we take an area within, a rectangle within our lamina, okay, and we evaluate its density, rho of xy, along whatever this particular area is, right? It's delta x, delta y, okay, right? And then we add up all those areas and times those densities, right? So each one of these boxes, say for example, has has a mass m equal to rho of xy, or we call it xi star, yi star, times delta x, delta y, okay? You go in, you sum them all together, you take the limit as n goes to infinity, like we've done with integration, and what we end up with is we end up with the double integral, right? Where this double integral gives me the area, and then we're just going to basically multiply it then through by the density. So there's our mass. That's actually going to end up being equal to our mass. All right. So let's go in and we're going to find the total mass. We're going to consider a lamina R with vertices 0, 0, 0, 3, 3, 0, and with a density of rho of xy equals xy kilograms per meter squared. And we want to find the total mass. So what I'm going to do is I'm going to draw my region because I'm going to actually need to figure out what D is. We need to figure out my region D. Okay, and so I've got 0, 0, got that corner. I'm going to have 0, 3 right here and 3, 0. So we've got an isosceles triangle. Okay, there's my region. All right, and what I'm going to need to do is I'm going to need to figure out what this value right there is, and that is going to end up being y equals, and this is going to be negative x plus 3, which equals 3 minus x, right? You can go in and just find that line. There's the line. And so consequently, what I'll do is my region D is going to equal the set of all xy such that we're going to have y is going to be greater than or equal to 0. Because notice, okay, there's my y, the x-axis, so y greater than or equal to 0, less than or equal to 3 minus x. And then we'll establish that x has got to be greater than or equal to, and it's going to go from 0 to 3. So there's our D. So consequently, what we'll do to set up our integral is we're going to integrate, okay? And let's do 0 to 3, so that's our x's first, or excuse me, our x's second, our y's first, and then xy, dy, dx. Okay, this ends up equaling, right? Integrate with respect to y first, so we're going to get the integral from 0 to 3, and this is going to be x times y squared over 2 dx, and that'll be evaluated from 0 to 3 minus x. Okay, and that'll equal then the integral from 0 to 3, okay, and that'll be x times 3 minus x squared over 2 dx. Okay, 3 squared over, that's it, okay? And so this will then equal 1/2 the integral from 0 to 3, and this is going to be then 9x minus 6x squared plus x cubed dx, and that'll then equal 1/2, and that'll be 9 over 2 x squared minus 2x cubed plus x to the 4th over 4, evaluated from 0 to 3. We'll plug that into a calculator, and that ends up giving me 27 over 8. And so that's the total mass. Notice, basically, big issue here, figure out what our region is, D, okay? Writing it in terms of like y in this case, or x if we wanted to make it type 2, or excuse me, yeah, putting it in terms of x, or putting it in terms of y if we wanted to make it type 2, okay? So we find the area of our region being represented by the integral, the double integral, and then we have our density function. We're going to evaluate over that area. Now we need to talk about moments. And if you remember in our earlier conversation about moments, if we talk about mx at its basic is going to end up being m1 y1 plus m2 y2 plus ... mn yn. Okay? When we had actually a constant density, all right, then what we ended up with is we actually ended up with something that was a little bit more, maybe complicated. Not really all that complicated, but that was, it didn't seem as straightforward. When we talk about it now with respect to the double integral and non-constant density, it actually turns out that it actually, I think, simplifies. All right, so our integral around a region R, okay, we want to imagine that we've got, what we're going to do is we're going to have, this is, and we're going to call these MIJs. Okay, MIJs just meaning that they're masses in 2 dimensions. So we got MIJ, that mass, whatever it is, because it's got a different kind of mass, times, and then our Y value, Yij, for that same mass. So whatever the center of mass is, so this is like the center of mass for the rectangle, and this is the mass, okay, and we go through and we basically multiply all those together, right? We're going to multiply them all together and then add them all together, just like we did here, okay? So if you imagine, like, we'll get a 2-dimensional region, okay, and we imagine in this 2-dimensional region, we've got this figure right here, and this figure is some rectangle, we call it the rectangle Rij. That's the name of the rectangle. It's got a mass. Its mass is Mij, is the mass of Rij. And then it's got a center with respect to the x-axis. Excuse me, a center with respect to the x-axis, which is some y value. So this Yij, okay, is the center with respect to y, or excuse me, with respect to x axis for Rij. Okay, so all we've got to do is just multiply the 2 of these together. Okay, we just go through, we multiply the 2 of them together. All right, and so what you see is you get this thing, it's the sum, right? I equals 1 up to k, and then we have j equals 1 up to l, I guess is what we'll utilize. All right, and so our my is just going to equal that, or excuse me, mx is going to equal these 2 sums, and it'll be our Mij, right? This mass times this location, Yij. We just add them all together, right? We just go through and we add them all together. And then all we do is we take a limit, right? Okay. The limit as, so if we kind of imagine that we're going to go through for the actual moment. So this is the approximation for the moment. The actual moment then is going to equal the limit as I and j, or excuse me, as k and l, our top values, these ones here, k and l, as k and l go to infinity of Mij, the sum, the double sum, Mij, Yij, right? Just the sum, all we're doing is, again, we're just doing this. That's all that's saying. Is sum up all of the masses times the masses times the y coordinate. All right, and then this ends up giving me the double integral, okay, over whatever region D we're looking at, of y times rho of xy, and then this is going to be dA, okay? So this is the area, this is the density. The 2 of those multiplied together, they end up giving me the mass, okay? And then y, that's your location. So you can see that actually, like in this case, mx is a lot more, it kind of seems much more straightforward, okay? Basically, it's going to be y times the density function times the dA, so that in this case, because we're using rectangular, it's going to be dx dy, or dy dx. Now let's look at my. My, okay, again, my, if you remember, if we look at it for like discrete points, is going to be m1 x1 plus m2 x2 plus dot 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 plus mn xn, right? We're just going to add up, we're going to multiply the masses times the location, mass times the location, add them all together, just like we did before, okay? But now, what we're imagining is, now we've got this lamina, we've got our rectangle, we've got Rij, our rectangle, okay? It's got a mass, again, it's got Mij, its mass, okay? Which is equal to rho of xi, yi, okay? Xi, yi star, whatever it is, times this area, so it's delta x, delta y, and we'll get into that later, Okay, but that's basically the idea. And then we've got a location now, and this location is with respect to the y-axis, okay? And that's going to end up being xij. That's location with respect to the x-axis. Or with respect to the y-axis, excuse me. Right, so it's got an x, so it's with respect to the y-axis. So this my then is going to be, if we kind of approximate it, we want to get lots of these boxes. It's going to end up being the sum I equals 1 up to k, the sum j equals 1 up to L, mij, yij, okay? And if we, want to now kind of get the most concrete way of writing this, the most, if we're going to take the limit to infinity so we can get our integral. So we got the limit as k and L go to infinity of that double sum. Okay, same thing as we have here. Double sum mij, yij. And that ends up equaling now, we're going to get, right, okay, if I rewrite this, and I'll just go a step further than I did here, I've got the integral over the region D. Yeah, and this actually should add in a delta A, just to be rigorous. This actually needs a delta A. Or no, actually, that's it. Okay. We're then going to we'll replace the MIJs, okay, with MIJ ends up equaling the density times the area, so that's delta X, delta Y. And so what we end up getting, or you'll also see this written as delta A. So what we end up getting is we end up getting the double integral over D of X times rho of XY dA. Okay? So again, it's now just location, all right, density, area. Finally, since that gives us, these are the integrals that we need, okay, then our centers of mass, x bar, is going to equal my over the mass, and then y bar is going to equal mx over the mass, okay? And so what we've seen, what that will look like then is my is the double integral, okay, over d of x rho of xy dA over the integral, the double integral over d of rho xy dA. Okay, so my over the mass, and then y bar is going to end up equaling the double integral over d of x rho of xy dA divided by the double integral over d of rho of xy dA. Okay, and that ends up giving us our center of mass. Now, what we can do now is we can talk about finding a centroid of a region using a double integral. So remember that the centroid of a region, it's the center of a mass for a region with a constant density rho. Just as we did with areas, we can find areas using the double integral. The same is true for the centroid. So what we're going to do is we're going to look at those formulas that we have for the moments and for the mass. So remember, the mass is equal to the double integral over d of rho of xy dy dx. And if we make rho constant, then this is going to end up equaling rho, right? If rho is constant, we get rho times the double integral over d of dy dx. Okay? Right? And this is just the area of the region times its density, done. Okay? Now the moments, mx, we'll start out with mx. Remember, that's going to be the double integral of d times y, rho of xy dy dx. And so if rho is constant, we're going to end up with rho, because we can just pull it out. We're going to pull out rho times the double integral of d of y dy dx. Okay? And my, then, you can probably predict what this is going to look like. It's the double integral over d of x rho of xy dy dx. And that's then going to give me rho times the double integral with respect to d of x dy dx. Okay? So, given that's the case, what we can do now if we want to find our centers of mass, right, is we've got x bar is going to equal my over m, and what's going to happen is that the rows are going to actually cancel. And we saw that actually when we did it in with single integrals. D x dy dx over rho times the double integral over d of dy dx. And so canceling out our rows, we end up with the double integral over d of x dy dx divided by the double integral over d dy dx. Okay, so that is that actually is our center of mass. And then for with regard to the x-axis, and then y bar, which is mx over m, is going to equal, along the same lines, it's going to be the double integral over the region d x dy dx divided by the double integral with respect to d of dy dx. And so our center of mass is going to be given by x bar and y bar for the centroid. So notice it's not going to be dependent upon the density. The density is not actually going to be any part of our finding of our centroid, which is our center of mass for a lamina of constant density. So like, for example, if what we did was we went in and we said, okay, well, now I want to find the centroid for our triangular region, the one that we discussed earlier. So what we're going to do then, we've got the double integral. We'll find our mass first. M equal the double integral over d, and this is just going to be dy dx, which equals the integral from 0 to 3 and 0 to 3 minus x dy dx, which equals then, we're going to get the integral from 0 to 3, 3 minus x dx, which ends up equaling 3x minus x squared over 2, evaluated from 0 to 3. And that ends up equaling 9/2. Now we're going to go in and we're going to take a look and see if we can find our mx and my and mx. So my is going to equal the double integral from 0 to 3, 0 to 3 minus x dy dx. Okay, so that's going to then be, we'll evaluate first with respect to y. So it's going to be 0 to 3, and it'll be x times 3 minus x dx, which ends up equaling 3x minus x squared over 2, evaluated from 0 to 3, which we already saw was 9/2. And then we'll find mx, which equals the integral from 0 to 3, the integral from 0 to 3 minus x, y dy dx, and that equals then the integral from 0 to 3, and we're going to get y squared over 2, evaluated from 0 to 3 minus x, okay, which equals the integral from 0 to 3 of 3 minus x squared over 2 dx, which equals 9 minus 6x plus x squared divided by 2, evaluated from, and that's the integral from 0 to 3 dx, which equals, well, that's going to give me then the integral 0 to 3, 9/2 minus 3x plus x squared over 2. And this then equals 9/2 x minus 3/2 x squared plus x cubed over 6, evaluated from 0 to 3. And when we figure that out, do a little math, we get 9/2 as well. So x bar is then going to equal 9/2 over 9/2, because it's my over m. So that equals 1. And y bar is going to equal 9/2 over 9/2, because it equals mx over m, and that equals 1. So the centroid in this case is 1, 1. The center of mass for this constant density region is going to be 1, 1. And that makes sense. Okay, so there's your centroid. And that makes sense given the fact that we're going to get a different center because our density is evenly distributed versus the one that actually is going to be dependent upon x and y. The one that's going to be dependent upon x and y, we saw at center of mass. Okay, there it is at center of mass, 18 over 15, 18 over 15, which, by the way, we could actually rewrite as 6 over 5, 6 over 5 if we wanted to. And the difference has to do with the fact that the density of the region that we're looking at is different based upon the density changes over the area in the first example and does not change over the area in the second. All right, so now let's talk about moments of inertia. So the moment of inertia of a particle of mass, m, is mr squared, where r is the distance to the particle from the axis, whichever axis that we're looking at. So it could be the x-axis, could be the y-axis. So if we have multiple masses and we want to know the moment of inertia for a region r, it's going to make sense that what we want to do is we want to add up all of those moments of inertia in the region. Okay, which, if you kind of think about it, given what we've done before, and I almost feel redundant about the whole thing. I just feel like I keep saying the same damn thing over and over again, but I'll say it again. We're going to calculate the moment of inertia for one particular region and add it up for the entirety of the region that we're looking at. Okay, so you can imagine, since that's what we've been doing, that we're going to eventually end up with a double integral. That's the thing that we're going to end up with. Okay, and from a physical standpoint, a practical standpoint, what the moment of inertia does is it's going to measure the tendency of the mass to resist a change in rotational motion about the axis. So it ends up having like some physical properties that end up being very powerful when you're doing physics. So we kind of do want to figure out the moment of inertia. Now, what we're going to see is that we're going to see that it's very closely related to moments. All right, so it's going to end up being very closely related to moments. And so we're going to call our moment of inertia, we're going to start out with Ix. And so this is about the x-axis. It's about the x-axis, okay? And what we're going to see then is if it's about the x-axis, then it's going to be with respect to like some y values, right? We'll imagine we've got a rectangle here, okay? This is the one about the y-axis, so it's got like some yi right here, okay? And it's going to be multiplied by the mass, and so it's the mass of the region. Mi, we'll call it Mij. So this region is Rij. Okay, we got Mij. Mij is going to end up equaling rho of xi star, yi star, right? Okay, we got our stars here, and then we've got delta x, delta y. Okay, so Ix is going to end up being, so like the I, we'll call this Ix for the Ij region is going to just end up being, right, it's going to be yi star, or we call it actually yij star, squared times rho of xi star, yi star, delta x, delta y. Okay, so basically what we've got here, here's the mass, here's the point location with respect to the x-axis, and then what do we do? What we do is we imagine we've got an entire region. There's our region, and so we're going to go in. We're going to add them all together. Okay, we're going to take the limit as k and l go to infinity. All right, like as we get more and more and more of these regions that are smaller and smaller and smaller in size, right? And we get Ix ends up equaling the double integral over the region D of, in this case will be y squared rho of xy dA. So whether or not we use dy dx or dx dy doesn't really matter. Same principle. If we imagine now, instead, here's xi, right? So this is xi, yi is the center of the region. So we get iy, okay, so this is about the x-axis, or excuse me, about the y-axis. So this is our x's, is going to equal the double integral over the region D of x squared rho of xy dA. Okay? different quantity, same exact process. Totally the same process. And you can imagine like why it is that like integration is so powerful. Like integration is so powerful because I mean, you know, essentially we've got two different quantities, okay? They have different properties, different reasons for why we're interested in them in physics and other applications. And all they really are is just, they're just double integrals, right? We're just going to take some double integrals and that's going to give us these values. And it's going to make our lives, you know, kind of, it basically is we can utilize one concept to go through or one operation to go through and generate tons and tons of concepts. So let's take a look at an example. So let's imagine we have a triangular region R with vertices 0, 0, 2, 2, and 2, 0, and a density function rho of xy equals xy, like we had before. Let's just set this up. Let's set up our moments of inertia. So I'm going to draw my picture. Okay, just in general, I like to draw things. Okay, got 2, 2. So there's one of our values. Okay, we got 2, 0 there, and 0, 0. So there's our triangular region. All right. So y is going to be greater than or equal to 0 and less than or equal to, okay, this is going to end up being y equals x. Okay. So x and x is going to be greater than or equal to 0 and less than or equal to 2. Excuse me. So those are the bounds for our integration. So we're going to integrate. We got 0 to 2. Put our constants in there. We got 0 to x then. And then, so this is, we'll do ix first. Ix is going to equal then y squared. And this is times xy dy dx. Okay, there we go. So that's our y squared times our density function. And then iy is going to equal the integral from 0 to 2, 0 to x of x squared times xy dy dx. And those are our moments of inertia. You just go in, evaluate the double integrals, there you go. All right, so let's now take a look at the mass moments, centers of mass, and moments of inertia in 3 dimensions now. Now what we're looking at is we're looking at volumes that are not constant, that don't have necessarily constant density. Again, if we talk about, you know, the mass of a region, the mass in this case is going to equal the volume times the density, which is the one that we're probably more associated with because we live in 3 dimensions, volume times density. And so you can see that that's what's going on right here. That's that volume times the density, or we're, you know, kind of approximating that density over this entire region over its volume. So we've got that triple integral, rho of xyz dv. It's moments about the xy plane, the xz plane, and the yz plane. So the xy plane, if you think about this, so the xy plane, we'll look in, we've got, we're going to do this in 3 dimensions. Okay, down here. So if you think about it, here's this xy plane, and so if that's going to be, right, our axis of symmetry, then what we're talking about is we're talking about our z's, right? Our z's are going to be the things that we are going to be separated with respect to the xy plane, and hence why we got the z of rho of xyz for xy. Xz, you can kind of imagine, xz is going to be, it's separating out the y's, so xz is going to be separating out the y's, okay? And so hence that's why it's y rho of xyz dv. And m of yz is going to be separating out our x's. So if you kind of think about this, look at this, you've got xy has no z. So that's why that's how you know that your z's are going to be in for the moment around xy. Your xz is going to be no y, okay? And so consequently it's going to be around the y-axis. And then yz is going to be no x. And so consequently that's how we know that we're going to have our x's in m of yz. Our moments then are going to be, as we kind of like think about them, x bar is going to be m of yz. So it's going to be the one with the x in it. Okay? And y bar is going to be m of xz over m. So we're kind of developing our center of mass for this volume. And z bar is going to be mxy over m. Same kind of like, same basic idea here, okay, as we had in 2 dimensions. We just added in basically another variable here. And then, if we look at our moments of inertia, remember that this is actually r squared, or mr squared, so that's mass times distance. And so, if you think about Ix, the distance from that x-axis is going to be y squared plus z squared. Okay, actually, this distance, right, is going to be the square root of y squared plus z squared. And so if we square it, distance squared is going to end up being just y squared plus z squared. For example, distance with respect to x. We do the same thing for Iy. That's going to be x squared plus z squared. And Iz is going to be x squared plus y squared. And so this actually gives us, a set of formulas that we can utilize in order to find our masses, our moments, our centers of mass, and our moments of inertia for 3-dimensional volumes. Okay, so let's take a look at one more example here, and then we'll finish up this video. So let's suppose that Q is a solid region bounded by x plus 2y plus 3z equals 6, and the coordinate planes, and has a density rho of x, y, z equals x squared y, z. Okay, so we're imagining that we've got a coordinate plane, okay, or we've got this region, this triangular prism, or a solid region, all right, and we'll first start out with, we're going to have, if x and y are equal to 0, okay, so 0 plus 2 times 0 plus 3z equals 6, that means z is going to equal 2, so this point right here, that's going to end up being 0, 0, 2, that's one of our vertices. We'll go in, we'll make x and z equal to 0. So 0 plus 2y plus 3 times 0 equals 6. So 2y is going to equal 3. So we're going to get the point 0, 3, 0. There's our second point. So 0, 3, 0, let's say put it right there. 0, 3, 0. Okay. And then finally, if we let y and z equal to 0, we get x plus 2 times 0 plus 3 times 0 equals 6, and so consequently x equals 6. So a little bit longer over here. We'll make it out there, and just there it is, and that's going to end up being 6, 0, 0. Connect the dots, and what we get is this is our triangular region. Okay. Couple things that I want to do here is I'm just going to do the setup here for our total mass. Then we're going to find our moments. And then we're going to find our moments of inertia and our centers of mass. So we look here, and the first thing that I have is I have this plane. So let's actually go in and write it in terms of z. So let's find our bounds for our integral, because that's going to be the hardest thing. So 3z is going to equal 6 minus x minus 2y. Okay. And so z equals 2 minus 1/3 x minus 2/3 y. Okay. And so we're going to go, it's going to go from 0, z equals 0. So that bounds is 0 less than or equal to z less than or equal to 2 minus 1/3 x minus 2/3 y. Then we're going to go out and let's take a look at this triangle down here. So this triangle, if we kind of draw our triangle out, the triangle is going to look like this. Here's 6, 0, and here's 0, 3. Okay, so there's the triangle that down there, and that's going to be our region D. And if we write this, what is this region? This is going to end up being y equals negative 2x, right? Because we're going to go, oh, actually negative 1/2 x, because this is going to be up 1/2. So negative 1/2 x plus 3. So my y values are going to go from y greater than or equal to 0, less than or equal to negative 1/2 x plus 3. Okay, and that's that region right there. Okay, or at least that's that, not that region, it's rather that line right there. And then finally, our x values, x is going to be greater than or equal to 0 and less than or equal to 6, because those are the values for x. They go from 0 to 6. So that gives us the balance for our integration. Okay, so we'll take a look at our our density. It's going to be x squared yz. And so if we start out with our mass, okay, the mass is going to equal the integral. We'll do 0 to 6, 0 to negative 1/2 x plus 3. And the integral from 0 to 2 minus 1/3 x minus 2/3 y. And it will then be x squared yz. X squared yz. And then we actually wrote this as, excuse me, dz, dy, dx. Okay, that's your mass, right? Density, area. Now let's find our moments with respect to each one of the planes. So we'll start out with m of yz, okay? M of yz is going to equal, same bounds, same region, 0 to 6, 0 to negative 1/2 x plus 3, 0 to 2 minus 1/3 x minus 2/3 y. And then notice no x in there, so this is going to end up being x times x squared yz, dz, dy, dx. M now of xz, so no y in there, is going to equal then the integral 0 to 6, 0 to negative 1/2 x plus 3, 0 to 2 minus 1/3 x minus 2/3 y. And this will be y times x squared yz, dz, dy, dx. And then m of xy, notice that there are no z's in there, so this is going to be 0 to 6, it's going to equal 0 to 6, 0 to negative 1/2 x plus 3, 0 to 2 minus 1/3 x minus 2/3 y. And this is going to be then z times x squared yz, dz, dy, dx. Woo! All right, there's like some sweat coming off me. Goodness. Okay, so there's our moments. I am going to forego. I'm just going to say that x bar is going to equal myz, then over m. Y bar is going to then equal mxz over m, and z bar is going to be the moment m x y over m. And there's our center of mass. And then actually it's going to be ix, the one with respect to the x-axis, is going to be the integral from 0 to 6, 0 to negative 1/2 x plus 3, 0 to 2 minus 1/3 x minus 2/3 y. And this one is going to be then y squared plus z squared. Notice because it's x, so it's going to be the distance is going to be y squared plus z squared. And then we'll square it. Times x squared yz, dz, dy, dx. Iy, and now I fully understand why they do this. We're going to just, it's going to be the integral over our region, we'll call our region Q. The region Q, and that is going to be then x squared plus z squared times x squared yz, dz, dy, dx. And then iz is going to equal the triple integral over q of x squared plus y squared times x squared yz, dz, dy, dx. And that is our moments of inertia. What you do is you go in and then you go and you'd integrate these. Actually, what all of us do, is we go in and we'd use a symbolic calculator like Mathematica or Maple or Wolfram Alpha or Symbolab, which is one of the ones that I use. And what we do then is we plug this thing into there and we get out an answer. We know how it's set up. We already know how it's done. Okay? Assuming that you do, after this course, right? You go in, you plug this thing into the symbolic calculator, you get out your answer. Bob's your uncle and you're done. Okay? All right. So let's kind of review a little bit about our our moments, and our centers of mass. Okay, so for our purposes, okay, when we're talking about moments of inertia, moments, centers of mass, masses, the first big thing to remember is that a mass is the density times the area. Okay, so we represent that as a triple integral or as a double integral over an area. Okay, and we have a density function that we evaluate at every point in that area. Okay, and so we've seen that it's very similar to what we've done before. Basically, you're just like, okay, it's rho of xy dy dx. There's my mass, right? I take the double integral. When we talk about moments, again, we're still just adding or accumulating. So our moments are just going to be either x rho of xy or y rho of xy. And we're going to take the double integral with respect to those as well. Okay? Or, you know, in the case of volumes, we might take a triple integral, okay, for x, y, and z. Right? But you should be noticing that there's a relationship here. Then when we talk about our centers, right, our x bar is my over m, right? Okay, or x bar in 3 dimensions is myz over m, right? It's the other two that we don't have over our mass, okay, and it's gonna have an x in that top integral, right? If we're looking for y bar, it's gonna have a y in that top integral. Right, so there's this consistency there that you want to kind of notice as you're going through and working through your problems and working through this work. Try and see if you can actually see some of the relationships here, okay, to all the different kind of formulas that we've shown. In addition to that, what I really want to like focus in on here for those of you who are interested in the math and really want to understand how the math and the physics relate is that essentially what we're looking at here is we've got a quantity, an amount, a density, okay, which is evaluated over a region. It changes with that region. And what we're doing is we're trying to add up, right, that mass times the density over the entire region if like it's a moment, or we're trying to add up the density over the entire region if we're looking at the mass, or we're trying to add up those moments of inertia, okay, accumulating, adding up, pulling them all together, and then that's what the integral does. It accumulates all of them over the entirety of the region, and that's basically the notion of what integration is. Whether or not we're integrating in 2 dimensions, where we're integrating over areas, or we're integrating in 3 dimensions, where we're integrating over volumes.